Hello student, in this lecture we will discuss one more problem with the help of dynamic programming, and the name of the problem is 0 knapsack problem. In 0 knapsack problem we have n number of items, and let Vi denotes the value of the ith item and Wi denotes the weight of the ith item. Now suppose you are given a knapsack capable of holding the total weight W. Now our goal is to use the knapsack to carry item such that total values are maximum. That means we want to find a subset of items to carry such that the total weight is at most the total value of the item as large as possible. Now we cannot take parts of the item, that means either we have to consider the item whole or nothing. That's why it is called 0 knapsack problem. In a formal way, or in by using mathematical expressions, we can say that for a given W which is greater than 0 and two n tuples of positive numbers v1, v2, vn, that means this is used to denote the values of the item, and one more tuple of size n that is used to denote the weight of the items. We wish to determine the subset T such that it maximizes the value Vi subject to the weight of the item collected is always less than equal to the capacity of the knapsack. Okay, so to maximize this, and this is a constraint on the weight of the items. Now if we do the brute force approach or analysis, if there are n number of items, for every item we have two possibilities: either we may pick that item or leave it. So if we have n number of items, then total number of possible solutions or total number of possible subsets would be 2's power n, which is exponential. And every solution of this is a valid solution, but we have to optimize our solution on the basis of the value attained after the item selected. That's why it is an optimization problems, and brute force analysis would get us order of 2's power and time complexity, which is an exponential complexity. That's why we are going to use dynamic programming in this problem. Okay, now for the dynamic programming we have to follow some steps. As per the dynamic programming rule, we have to follow 4 steps, and first step says we have to define the subproblems, or we can say we have to characterize our solution. So for that purpose, let's say we construct an array V, which is 2-dimensional array, or we can say table, and the size of the this table is n into w, n plus 1, or exactly, if I exactly say n plus 1 into n plus w n plus 1, or we can say if n and w are sufficiently large, then n into w. Now for I which lies between 1 and n, for w which lies between 0 and w, the entry viw will store the maximum combined value of any subset of item 1 to I of combined with at most w. That means for a particular I, if I is something, that means we have, first of all we have to make a order of items. That means item number 1, item number 2, item 3, and so on. And if we are considering the ith item, that means you can consider I items among the all available items. Okay, that means numbering from 1 to I, and W denotes the current weight being considered. So our problem converted into VIW is a maximum of subsets which follows this constraint. That means sum of the collective items is always less than equal to the capacity of the knapsack, current capacity of the knapsack, and we have to select item. We have to find out subset of ith item. That means by considering the ith item, I number of items, you have to find out the subset of that. If we can compute all the entries in this way, then array entry V and W will have our optimal solution. Now come to the recursive formula and recursive steps. In this step, what we do, we show that the solution of the problem is dependent on the solution of the sub problem. That means if we want to find out optimal solution of the original problem, then first of all we have to find out the optimal solution of the sub problem. Okay, so let's say vk denotes the value of the optimal solution. For that purpose we have two possibilities. It may be equal to vk minus 1w, that means solution attained by considering k minus 1 item, and by keeping the same capacity of the knapsack. What will happen? It will happen when weight of the kth item is greater than the capacity of the knapsack, current capacity of the knapsack. That means you can accommodate that. That means the solution is determined by excluding this item. Otherwise you have two possibilities. Those possibilities are, you may pick the item or you may drop that item. If you drop that item, that means you are voluntarily not considering that, then the solution would be vk minus 1w. That means current capacity of the knapsack doesn't change, but you are not considering the kth item. Okay. Or second possibility is that you are considering that kth item. If you are considering that kth item, that means value of that particular kth item will be the part of the solution, and the rest part will be decided by the k minus 1 item up to k minus 1 and the reduced capacity of the knapsack. So we have to check out these two possibilities, and which one provides the maximum value, that will be considered as the solution of this. Okay. We have already discussed that. Now let's discuss the algorithm. Okay. Now this is the third step. In third step we solve the problem in bottom up fashion. Okay. In the first for loop, this loop says if the capacity, if there is no item in the room, then it doesn't matter what is the capacity of the knapsack, the value added would be 0. Okay. Third loop says if you have n number of items, you are considering one by one, but you don't have the knapsack, in that case value attained will be 0. Now from line number 5 to line number 11 solves our dynamic approach. Okay, solves this problem with the dynamic approach. What it is, it uses that recursive formula we have previously discussed. Now what does it say? We have to change the capacity of the knapsack 0 to capital W, and now for every time, every value of W, every integer value of W, we have check out two things. If the current ith item which are being considered, if the ith item which is being considered has the lesser weight than the current capacity of the knapsack, that means that particular item can be considered. And if it can be considered, then the solution would be, it can be considered, then you have two choices. You may pick that item or you may drop that item. This is the situation when you pick that item, and this is the situation when you drop that item. And based on the value, which one is greater, you assign that value into VIW. Okay. And the else part of this deals when that condition doesn't hold. That means this condition doesn't hold. That means if this value is not greater than this, then the part of the solution will be this. Now if this condition fails, Wi is less than equal to Wi, that means Wi is greater than W. That means weight of the ith item is greater than the current capacity of the knapsack, that means you can't make it part of the solution. So in that case you are bound to leave that item, and the solution would be Vi minus 1 W, that means without considering that item. Okay, so capacity is W. Okay, if the capacity is W, then for first loop, this loop complexity would be order of W, and n denotes the number of items, so it for loop goes to n times, so it would be order of n. Okay, now from 0 to capital W it is order of W. Okay, so the cost would be n into W, because we are filling the n into W size table. So with the help of two for loop, so cost would be n into W, and this is much lesser than brute force algorithm, which takes order of 2's power n. Now let's discuss one example of zero knapsack problem. In this example we are considering 4 items, and capacity of the knapsack is 5, and these are the elements weight and benefit. This is weight W, and this is benefit V. W V, that means item number 1 has weight 2 and it has value 3. Item number 2 has weight 3 and it has value 4. Similarly, you can find out the value of each and every item. Okay, now let's apply our algorithm to this example. So as for the first loop, it says for W is equal to 0 to capital W, V0 W, that means value of I remains 0. It signifies that it doesn't matter what is the capacity of the knapsack. Well, if you are not considering any item, that means if there is no item in front of you, the value gain would remain 0. Okay, so it is 0 0 0 0 0 0. Okay, 0 0 0. Now come to the second loop. As per this loop, it says for I is equal to 0 to n, Vi 0 is equal to 0. That signifies that if the capacity of the knapsack W is 0, always remains 0, it doesn't matter how many items do you have, it would not provide any value to the solution. In that case it would remain 0, so it is 0. Now come to this logic. Now let's consider, we are considering item number 1. Okay, we are considering item number 1 and we want to fill this array or this column, and we are considering only single item, and for that single item we will change our knapsack capacity. Let's say if the knapsack capacity is 1, let's say if the capacity of the knapsack is 1, in that case if we want to accommodate this first item which has the weight 2 and the current capacity of the knapsack is 1, you cannot accommodate that. This signifies that this condition doesn't hold. Wi is no less than equal to W. So in that case this code will this else part will run. What it does, VIW is equal to Vi minus 1 W. In our case I is equal to 1 and W is also 1, so V11 is equal to V01. So what is V01? This. So this value will be used over here, 0. Okay. Okay, now move forward. Next time this capacity of the knapsacks becomes 2 and the item being considered is 1. So this time item current capacity is 2 and the weight of the item is 2. That means you can accommodate that. That means this condition holds true, and now it's true. We have to compute two things: Vi plus Vi minus 1 W minus Wi and Vi minus 1 W. So what is the value of Vi? Value 3. So it is 3 plus vi minus 1 wy. So what is the value of I? 1. Y minus 1 minus 1 0. What is w? 2. What is wy? 2. So v 0 0. So what is value of v 0 0 0? It is 0. Greater than vi minus 1 w. So v 0 1. Oh sorry, v 0 2. V 0 2. What is v 0 2? V 0 2 is vi minus 1. What is value of I? 1. So v 0. What is 2? So v 0 2. What is v 0 2? 0. So as we can see, this condition holds. So value of viw would be 3 plus 0. Okay, so it would be this value plus 3. This value plus 3. Okay. Similarly, when the current capacity of the knapsack is 3 and you are considering the single item, again it would get 3. Or if you increase further the capacity of the knapsack, now it is 4, and you are considering the single item, it will remain 3 and next 3. Now let's say now you are considering 2 items. Now if you are not now considering 2 items, item number 1 and item number 2, and the current capacity of the knapsack is 1, that means these two are, none of the items can be accommodated, that means the value remains 0. Okay, now if we increase the capacity of the knapsack, now it is 2, then we can accommodate the first item, that in that case the value would be 3. Okay, now come to second solution, next case. Now capacity of the knapsack is 3. Now we can not accommodate both items, but we can accommodate any one item. So if you accommodate the first item, the benefit is 3. If we accommodate the second item, the benefit would be 4. So we definitely will accommodate the 4. Okay. Now similarly, if the current capacity becomes 4, in that case we can accommodate the second item, the value would be 4. Now if the current capacity of the knapsack is 5, then in that case we accommodate both items, so capacity the value would be 7. Okay, now move further. This time we will consider 3 items, and as we have already discussed, with the help of 3 if the current capacity of the knapsack is 1, that none of the item can be accommodated, so it is 0. If the current capacity of the knapsack is 2, that means first item can be accommodated. Okay, so it is 3. If current capacity of the knapsack is 3, that means only second item can be accommodated, the benefit would be 4. Okay, now if the current capacity of the knapsack is 4, that means the third item can be accommodated only, that would result as a value 5. Now if the current capacity of the knapsack is 5, that means first and second item can be accommodated, and the benefit would be 7. Okay. Similarly, if the item if we consider the all items, this is 4 items, if the value of the capacity is 1, none of the item can be accommodated, it is 0. If the capacity is 2, that means first item can be accommodated. If the value capacity is 3, that means second item can be accommodated only. If the capacity is 4, and in that case only third item can be accommodated, that would result in benefit value 5. And if the capacity is 5, in that case first and second item can be provide the optimal solution, then in that case value is same. So like this way you can fill the whole table, and the last value which is filled over here provides the total benefit gain. Now come to the step 4, which is used to provide the construction of the optimal solution. That means how we get the optimal solution, that means which items are part of the solution, which are not. Okay, so to compute the actual subset, we can add an auxiliary Boolean array keep IW, which is 1 if we decide to take the ith item in otherwise it is 0. So this is the simple solution. The following partial program will output the element t. ठीक है. Okay, k is equal to w for I is equal to and down to 1. If keep I k is equal to 1, that means that index item is a part of the solution and will reduce the capacity of the knapsack. ठीक है. And we like this way with this for loop we can find out the solution. Okay, so complexity of the overall algorithm is order of n into w. Thank you very much.